Here's a strange kind of violence. A singer holds a note, just the right note, and a glass sitting quietly across the room shatters. She never touches it. So how does a sound, thin as air, break solid glass? That's resonance. To see it, we strip the problem down to the cleanest toy there is, a mass on a spring, and, for now, no friction at all, nothing to bleed the energy away. Left alone, it obeys one tidy law. Mass times acceleration plus stiffness times position equals whatever you push it with. And when you don't push at all, the right side is zero, but it still wants to swing at one special rate. That rate is the natural frequency. Call it omega naught, the square root of stiffness over mass. Stiffer spring, faster wobble, heavier block, slower. Every swinging thing has one, a rhythm baked right into it. Left alone, it just rings at omega naught, forever, at a steady amplitude. Now let's push. We drive the spring with a periodic force at some frequency of our choosing, omega. And here's the whole question of the video. What happens as we slide our push frequency toward the spring zone? As long as your push is out of step, omega different from omega naught. The answer stays calm. The motion settles into a steady swing at a fixed amplitude. Bigger, sure, but bounded. Trapped between two flat lines. It never runs away. But now watch that amplitude as a function of your push frequency. Far away, it's small. Creep omega toward omega naught, and the denominator shrinks towards zero. So the amplitude climbs and blows up right at the natural frequency. So what happens exactly on the knife's edge when omega equals omega naught? The old formula just breaks. You'd be dividing by zero. That's the math waving a flag. Something genuinely different is going on here. The reason is subtle and kind of beautiful. At that exact frequency, your push is in perfect lockstep with the spring's own free swing. So the usual guess is already a solution of the quiet equation. It can't answer the push. You have to multiply the guess by time itself. Solve it, and out comes the resonance response. F naught over 2 omega naught times t times the sine. And that little factor of t changes everything. The system still swings at omega naught, but the amplitude out front grows straight up with time. Linearly, forever. The swings just keep getting wider. There's no ceiling at all. The picture behind it is simple. Every single cycle, the force pushes in exactly the direction the block is already moving. A perfectly timed shove, over and over. Energy goes in, and with no friction, none comes out. So it just piles up, cycle after cycle, and the amplitude piles up with it. This is why marching soldiers break step crossing a bridge. A column stamping in perfect rhythm can hit the bridge's own frequency, feeding it a little more sway each step, until the swaying gets dangerous. Break the rhythm, walk out of step, and you break the resonance. Now, a word of caution. You'll often hear the Tacoma Narrows Bridge blamed on simple resonance. Careful there. That collapse was something subtler, an aerial elastic flutter, where the wind and the bridge's twisting fed each other. Related in spirit, but not the same clean push-in rhythm we've been drawing. Worth keeping honest. So that's resonance. Match a push to a system's own rhythm, and tiny nudges add up without limit, an unbounded answer hiding inside a friendly little equation. Find something's natural frequency, and you hold a surprising amount of power over it.